Good morning. Today we're going to look at using Excel to compute recurrence relation formulas a little bit quicker than by hand. So we know that if we can find a closed form solution, that's a really quick way to get to an answer for some number of time steps later. But maybe you don't know how to get a closed form solution, or if you do, you'd still just rather do it in Excel really quickly rather than solve for the closed form solution. So that's the focus today. And so the application that we're looking at, I'm going to zoom this in a little, is a particular crane population in Florida. And so the subtitle here is Hacking Chicks, which sounds kind of bad, but I'll explain that in a minute. So the basic idea is that there's this crane population, and it has an intrinsic birth rate, which in this case is indicated by the parameter b. And so basically a quarter of the cranes reproduce. And then there's a death rate associated with the population, and in this case it's 0.43, so about 43% of the cranes die per time step. And then there's this parameter h, which comes into play for the hacking part of the problem. So as you can see, the birth rate is much lower than the death rate here, which means that this population is in danger. So hacking chicks, what that is it's essentially just raising the chicks in captivity until they're of an age where their likelihood of survival is a little bit higher, and then releasing them back into the population. So that's what it means to hack chicks. It's kind of like a I don't know, a wildlife refuge type idea, right, where you just make sure that the young ones in the population are more likely to survive, so they're a little bit hardier or whatever. And so in this case, let's say that 5 chicks are hacked every time step and released back into the population. And then here I've indicated 3 different populations that all have different starting numbers. Right, so the first population is really, really tiny, so the cranes are almost extinct, and we want to see if we can help them out. And then the other one, we've got 50 cranes, and we want to see what happens under the same scenario, and same thing with 25 cranes. So before I actually begin inputting formulas into Excel, I want to just make sure that we have the basic recurrence relation down that we're going to use within Excel. So I'm going to do this in red, just so it's clear that this is a formula that's important. So I'm going to say the number of cranes, x, at any time step n, well, it should be whatever number we had before, plus the ones that were born, so b times x of n minus 1, because b is a birth rate, right, so it depends on the population at time n minus 1, minus the amount that died. So again, because that's a death rate, it depends on the previous population. But then we're also going to add in a fixed number of chicks. So the hacking is not our rate, it's just a flat number. So altogether we have x of n equals x of n minus 1 plus b times x of n minus 1 minus d times x of n minus 1 plus h. It looks like we can probably simplify that a little bit, right, if we just factor out all of the x of n minus 1s. So we have 1 here plus b minus d. So I'm going to go ahead and just rewrite all of this. 1 plus b minus d times that first x of n minus 1. Get rid of the intermediate stuff. Just so that it's a little bit quicker to type into Excel. Alright, so I'm going to go ahead and apply that formula for each of my populations. So for population 1, I hit my equal sign because I'm telling Excel that I want to actually compute something. And then I'm going to go ahead and put in 1 plus, and for B, I always want it to reference cell F3 in this case, so I'm going to use those dollar signs that we talked about. So $F, $3 means it will always reference column F, row 3. and then minus the death rate, which is always, always, always going to be in G4. So using my dollar signs again. Close that off. Multiply by the previous population. So I'm just going to click on the cell that contains that value. And then I'm also going to add the value that is hacked, which is always, always, always H3. And I just noticed that I mistakenly put G4 there, and we of course want G3. So if you're following along, be sure to fix that now. Alright, so I'm just going to double check. I've got 1 plus B is held fixed, minus D, which is held fixed, times the previous population, which I allow to vary. So when I don't use the dollar signs, then whenever I move to the next cell, it's just always going to reference the previous one. So we call this relative addressing versus absolute addressing, just in case you've ever heard those before. And then I add to all of that the fixed hacking number. So now that I'm happy with that, I'm going to hit enter. And a quick way to apply this formula now to all of the cells below it is that I see how there's this little blue box in the lower right hand corner. I grab onto that, I click and hold, and then drag it as far down as I want to go. So I'm going to go to 50 time steps. And so it looks like we end up, after starting with only 5 cranes, we end up with like 27 or 28, right? The decimal doesn't really make sense in terms of birds, but you know, it's basically somewhere in that range. Alright, so we're going to do the same thing for the next 2 populations, so I'm going to kind of zoom through these. So we've got 1 plus $F $3 minus $G $3 closed off times previous population plus $H $3. Now that I have a bunch of numbers in the column to the left of this, what I can do is instead of click and drag this down, I can just double click on the little blue box and it auto-fills for me, which is super nice. Then I'm going to do the same thing over here really quick before I look at what happened to population 2. I'm leaving you guys in suspense, although I guess you can look yourselves. So $F $3 minus $G $3 times previous population plus $H $3. And then again, just double click to autofill. Alright, so if I scroll down, looks like all of the populations are ending at roughly the same value, which is kind of interesting because they all started at different places, right? One was pretty tiny, one was pretty large, and one was somewhere in between. What I'm going to look at this really quickly is just look at it graphically. So I click to highlight all 3 of these columns. And once they're selected, I go to Charts. And I'm going to choose a line graph. You could probably do either line or scatter here, but I'm going to do line, and I want just a standard versus a marked one. And so now this gives me the 3 populations graphed over time. And so let's see, the red one started at 50, goes down to about 27, 28. Green one started at 25, rises a little to 27 or 28, and then stays there. And then the blue one started down at 5 and quickly rose up to right about that same value. So again, all 3 populations, regardless of where they started, ended up at the same place. Now, you might be asking, well, what if it had started either smaller than 5? Like, what if we had only started with 1 crane? Or if we had started with just a ton of cranes, so more than 50? What I'm going to do is I'm going to keep that green series, which starts at 25, but I'm going to change the one that started at 50 to be like 500, and then the one that starts at 5 to start just at 1 and see if anything changes. So let's go up to the top. What's great about Excel is I can just change it one place and everything else will adjust. So if I change this to a 1, hit enter, everything else has adjusted for me. And here I'm going to change this to 500, and everything updates. So let's scroll down now. And as you can see, our graph looks a little different just because the scale is now really weird on the vertical axis. But in the end, they're all still ending up at about 27 or 28 chicks. So mathematically, we call that point, this number that it's that all three populations are approaching, we either call that an equilibrium or a fixed point. And so that's essentially just some sort of value where once you get to it, you stay there. And then sometimes things can happen if you're a little off of the fixed point or the equilibrium, and that's what we're going to discuss in the next video. But for the time being, all you need to know is that we have seemed to find our steady state, which is termed equilibrium or fixed point. So I will see you in just a few minutes for a further discussion of that.